Hello, Math Humans. We're going to do 7.2a today. We're going to be talking about revolved solids. Particularly, we're going to be talking about the disk method. So our objectives are that we're going to find the volume of a solid of revolution, which are really cool, using the disk method. Unfortunately, you have to look at my art, which is not necessarily the best thing ever, so it's a good thing I have a day job. So let's say I take a rectangle, and I'm going to revolve that rectangle about the x-axis. So what it becomes, and again, here goes my gross artwork. So this is going to be, maybe I'll just do it right here. As I revolve this little rectangle, this is going to become the top, and then here's the depth, and then here is my disk. Isn't that pretty? Okay, so this is revolved around the x-axis. Well, what if I take the same basic image and I revolve it about the y-axis instead? So here's going to be my rectangle. Well, if I revolve that about the y-axis, that means that I'm going to end up with a hole. So it's going to look like a cylinder, and that cylinder is going to have this thickness. So there's going to be an inside. Like I told you, it's a good thing I have a day job, right? Well, what if we did something that's a little bit cooler looking, and I took maybe a curve. So let's say I had a curve, and I did it from, I'll do that, A to B, and I revolved that guy around the x-axis. So you'll notice that I'm drawing my little arrow to show which axis it's being revolved about. So I'm just going to add some information to our drawing before I try to sketch it. Notice that I would have a dx, which is going to be important because I'm revolving it about the x-axis. And on this one, the shape, so let me give myself some parameters. Ooh, that's going to be gruesome. So here's going to be the base, and then here's the curve. Here's the curve, and it's going to create a vase. That's kind of cool looking. Alrighty, so besides my grotesque artwork, and I really appreciate those of you that are talented artistically, we're going to talk about what's called the disk method. Okay, and this is called a disk because there are no holes. We're going to talk about the washer method, something that has a hole, in our next video. But one of the things that we need to notice is that the particular shape is touching the axis in this example and in this one, which means that there is no hole. Okay, so in this one, I'm just going to write that the object is sitting on the axis of revolution. And the reason that that's important is it means no holes. Okay, alrighty, so let me go to another page. I'll stick with my black, I think, for right now. So let's say here is my axis, and I have a curve that looks like this. Notice that it's sitting on the x-axis, and I'm going to rotate about the x-axis. So here would be my A. We're going to call this point B, and I'm going to draw my representative rectangle, okay? And it's going to be a dx. So then the height of the rectangle, just like when we did the area between regions or between curves, the height of the rectangle, here's my little representative rectangle, is going to be capital RX. And we're going to get that by top minus bottom. Okay? So in this case, because I am revolving about the axis and my object is sitting on the axis, the top minus the bottom would be f of x minus 0 because that's the axis. Okay, and that would be my r of x in this situation. The equation is going to be pi because we're rotating about an axis, and so we're creating a solid of revolution. Okay, and I'm going to integrate from A to B because I have a dx, and it's going to be r of x quantity squared dx. Okay, well, what if I have my object And my curve is the same curve, kind of the same curve, crappy drawing. But this time I want to revolve it about the y-axis. Well, now I have a sideways, so this is my dy. I have a sideways rectangle. Notice that the rectangles are perpendicular to the axis of revolution, and I'll write that down. So my rectangle is perpendicular to the axis of revolution. That will change later in the chapter. Okay. Well, since I'm going to have a dy, that means I'm going to integrate from bottom to top, so I'm going to call that CD. So then my volume is going to equal pi, the integral from C to D, R of y, quantity squared dy. So again, it's the same basic formula. The only thing that's really changing is my axis of revolution. So now let's jump in with some examples. If I can find my pins, I buried them. So for example number 1, I want to find the volume of the solid formed by revolving. Your book actually has some really nice pictures of what this looks like, so their artwork is obviously much better than mine. So you can go and look at the pictures in Chapter 7. Mine are gruesome, but functional. So here's going to be our f of x is equal to the square root of the sine of x, trig, and the x-axis, okay? And that we're going to go from 0 is less than or equal to x is less than or equal to pi, and we're going to rotate about the x-axis. They always have to tell you in solids of revolution which axis you are rotating about. Alrighty, so I'm going to sketch my graph, and I'm only going from 0 to pi, so that means the sine curve is going to look like this. So this is 0 and this is pi. I'm going to have a vertical representative rectangle, so this is my dx, okay? So when I set up my volume equation, my volume is going to equal pi, and I'm going to go from 0 to pi, okay? And then, because this is sitting on the axis of revolution, my r of x is going to be the sine of x, technically minus 0, quantity squared, okay? So I wrote the 0 because this is going to become important later when we start having wholes, right? But for right now, it's going to be the sine of x and then quantity squared dx, okay? And then if I do that math in my grapher, I'm going to get that my solution is 2 pi. So the volume from 0 to pi is going to equal 2 pi. Alrighty, let's do our next example. Okay, throw papers on the floor. So example number 2. I want to find the volume of the solid formed by revolving. Again, all of the directions are going to be about the same, but it's nice to recognize, by revolving, what our words are going to say. The region bounded by, and we're going to have f of x is equal to 2 minus x squared, and g of x is equal to 1 about the line y is equal to 1. So this one's actually going to be a wee bit different, and it's really cool. So let me draw my axis. So here's my axis. This is the same thing as a negative x squared plus 2. So if you're doing it by hand, it makes it easier. So this is 2. And so here's the upside down parabola. And then g of x is equal to 1 is going to be this line. So I'm going to write this as g of x, and I'm going to write this as f of x. Okay? I'm rotating about the line y equals 1. Okay? So I'm rotating about this line. So I'm scribble that out. Okay? There's the 1. here's going to be my axis of revolution, so it's a dx, okay? Alrighty, and then I'm going to do my math. So again, notice that my object is sitting on the axis of revolution. This is a hole, and for right now we don't have to worry about it because my object is sitting on the axis of revolution. So r of x, if you'll remember, is the height of my representative rectangle, and that's going to be my f of x minus 1, top minus bottom. Okay, so this would be the top, and this is the bottom. Okay, so then my r of x is going to equal 2 minus x squared minus 1, and if I clean that up, I'm going to get a negative x squared plus 1. Okay, so now I'm going to write my volume equation. My volume is equal to pi. I'm going to integrate, and I need to find those points of intersection, and they are a negative 1 and 1. And again, I'm assuming that you can find those. So I'm graphing from a negative 1 to 1, and I'm graphing a negative x squared plus 1 quantity squared dx. And I do that math in my grapher, and I'm going to get 16 pi over 15. Alrighty, I do want to point out that if I had felt so possessed, because this image is symmetric about the y-axis, I could have done that the volume is equal to pi, integrate from 0 to 1, and double it of a negative x squared plus 1 squared dx. So remember that you always have options when you're setting up your problem. All right, for example number 3, again, we're going to have a slightly new situation. So for example number 3, I want to find the volume of the solid formed by revolving the region, and in this one, we're going to revolve the region about the y-axis, which makes our party a little bit different. So we're going to be given y is equal to x squared, y is equal to 4, y is equal to 9, and then x is equal to 0. So if I put all of that information on a graph, okay, so I'm going to have y is equal to x squared. I'm going to do that in a different color. So here's my parabola. And then I have y is equal to 4, okay, so 1, 2, 3, 4. So this is y is equal to 4, and then I'm going to have y is equal to 9, so that's up there. Y is equal to 9. X is equal to 0 is here. So this is the region that's being revolved about the y-axis, which means that I'm going to have, because my representative rectangle has to be perpendicular to the axis of rotation, a dy. Remember, this is 4 and this is 9. And because I'm revolving about the y-axis, it's going to be the same thing as our area of a region. It's going to be right minus left, okay? So my volume is going to equal pi. I'm integrating from 4 to 9. And now I'm just going to start setting this up in here instead of writing it. But I notice that if I'm going to have a dy, this needs to be in terms of y. So if I have y is equal to x squared, then that's going to become x is equal to the square root of y. So notice that I didn't do plus or minus because my region is in the first quadrant, so I'm only taking the positive root. So then as I set this up, the right curve is going to be the square root of y. The left curve is going to be 0, quantity squared dy. Okay? Notice then that this is going to be the volume is equal to pi integral from 4 to 9 of y dy, and that's going to be 65 pi over 2. Alrighty? If you're using your calculator to put this in, the pi goes first, and then you do math 9. Alrighty, I have one more example for us. So let's do example number 4. And this one's going to say, find the volume, same directions, find the volume of the solid figure formed by revolving around the line x is equal to 2. So we're going to be given y is equal to x cubed, y is equal to 0, and x is equal to 2. These are the equations that are going to define our area. So as I graph this, here's my axis. I have y is equal to x cubed, which is this guy, okay? And then I have y is equal to 0 and x is equal to 2. So if this is the vertical line, x is equal to 2, that point is going to be 2, 8, because 2 to the third is 8. And so this is going to be my region that's being revolved, and I'm going to revolve it around the line x is equal to 2. So this is a cool situation because my vertical axis has moved. Again, I'm going to have a dy, okay? Since I have a dy, I need to rewrite this equation. So x is going to equal the third root of y, okay? It's always going to be right minus the left. So when I set up my volume equation, here's the pi. I'm integrating vertically, so I'm going to integrate from 0 to 8, okay? And then it's going to be the right 2 minus the left, the cube root of y, quantity squared, dy. So then I'm going to simplify this a little bit. Actually, there's nothing to simplify because that's a nice pretty little equation, and I'm going to get 10.053. Just in case you haven't thought of this, when I put this in my grapher, I'm not going to put in the variable y because that just makes my life miserable. So in my grapher, I'm still going to use my x variable, but I'm setting the problem up to show that I'm integrating vertically. Alrighty, that is it for today, my dears. I will see you soon.